next speaker is Tony Bartolotta, Bayesian updating in thermodynamics.
So first I'd like to thank you for inviting me here. This is my first conference involving any philosophy of science. So I want to be talking mostly about Bayesian updating and the role it can have in thermodynamics. So this is going to be more of a, I guess, philosophy of thermodynamics type talk. And I want to address a few simple goals. So most of this talk will be based on a paper that I wrote with Sean Carroll, Stefan Leichenauer, and Jason Pollock a few years ago. And the question is, why do I want to consider Bayesian updating in thermodynamics? So generally speaking, we're looking at something such as Maxwell's demon. It might be acting on a system. We're interested in including observers with a thermodynamic system, in which case the idea of what the observer's knowledge is generally relevant. And if it's a sort of rational updating observer, it'll be doing some form of Bayesian updating. And then, given this fact, does that change anything of how we think about the second law? Is there any new insight? Does it change how we think about the monotonicity of entropy increasing? And sort of coming from this perspective of non-equilibrium fluctuation theorems, does this Bayesianism give us a new class of fluctuation theorems or tell us anything new about the fluctuation theorems themselves? And can we apply this to things other than just, say, the entropy? So before diving in, I want to address sort of two competing views on entropy which kind of motivate this project. So if you think of it, entropy at the very high thermodynamic level, I have some fundamental differential relation here relating, say, work, temperature, entropy, volume, pressure, etc. You don't have to worry too much about what ds is. Okay, if I'm thinking about how the entropy changes, let's integrate like dq over t, I'll get some value for a change in entropy. I don't have to worry about microscopically what that means. It's some quantity that corresponds to some property of a macroscopic system. But if you're trying to get a little more into the weeds, there's two main definitions that we use. So I'm kind of putting words into people's mouths here, but we can roughly break these up into the Boltzmann view and the Gibbsian view. So Boltzmann, at least at some level, said you have macrostates. These macrostates define the entropy for a given microstate. In that sense, we have a very, quote, objective sense of what the entropy is, up to issues of where these macrostates come from. Meanwhile, you have a slightly different view, which is thanks primarily to Gibbs, and then later on sort of Shannon classifying how you do information theory properly, where we're talking about probability distributions over microstates. A system only truly has one microstate, but we have an idea that we might have an ensemble or some uncertainty there. And entropy then becomes related to our uncertainty in the underlying distribution. If you ever took a thermodynamics or statistical mechanics class, these are usually taught sort of in sequence of, oh, we do microcanonical, this is all done in Boltzmann, and then, oh, we're going to do some grand canonical, we should probably switch to Gibbs at some point. And you sort of switch back and forth interchangeably, not really noticing the difference when you go from microcanonical to something else. But that can lead to sort of sloppy reasoning because these can lead to contradictory outcomes if you're applying them sort of in the wrong sequence. So I want to look a little deeper at that potential tension between these two views. So I want to start with the Boltzmannian view. So roughly speaking, we can think of, we have some phase space, and we're going to break it up into macrostates. So maybe we have some tiny macrostate where we start off in, and there are bigger macrostates that we go into. So we know, thanks to the fact that, say, a gas has a large number of particles, the big macrostates are much larger than the small macrostates, sort of exponentially or at least like combinatorially larger. There are a lot of ways to distribute a gas across this entire room versus to pack it into a tiny corner of this room. There's a lot more potential ways for that configuration to be carried out. So if you accept that you have some macrostates, which presumably correspond to some variables that you want to measure or easily can observe, you can then talk about the entropy associated with each macrostate, which if you're following the Boltzmann view, you just say is going to be the log of the volume in phase space. So at that point, effectively, your entropy is objective at some level. Once we agree on macrostates, and we say that for any given microstate, there's an associated entropy with that microstate. A microstate passes through a macrostate, that's the entropy. We can debate about how objective this is because the question is, well, where did I get these macrostates from? Why do I choose this classification versus another classification? But we don't have to worry about that too much. So if we're thinking about evolution, just geometrically, if I'm sort of randomly walking around, I'm probably going to be drifting around into larger and larger macrostates. Generally speaking, if I'm randomly walking, it's unlikely I walk back into a tiny macrostate. So generally speaking, if you're thinking from this Boltzmannian view, entropy tends to increase, but it can always fluctuate. I could happen to stumble into a slightly smaller region of phase space, entropy might drop slightly. So in that sense, if you're thinking of it from a Boltzmannian view, the second law is really probabilistic. Entropy usually increases up to some fluctuations. But that we should contrast that with the sort of Gibbs or Shannon type view of what entropy is. So this time we're saying that we have some probability distribution over potential microstates for a system. I say that, okay, we have gas spread throughout this room. I have a vague idea as to what configurations are likely versus unlikely. Configurations where the gas is roughly equally distributed across the room is a very likely state. Configurations where the gas is sort of bundled up in one corner very tightly tend to be relatively unlikely. So I have some distribution over possible microstates. And given that distribution, I can define an entropy. So what we're going to be using primarily is the Shannon entropy, which is simply rho log rho, and then integrate that, and a minus sign to make it positive, which has some links to information theory, though the Gibbs approach isn't really. The Gibbs approach came before Shannon, so the information theoretic interpretation sort of comes later. And in this view, entropy really characterizes our knowledge of the system. If I know a lot about the system and say that, oh, we have some microstates and some probability of being in a microstate, and I know I'm almost certainly in some very particular microstate, I am very certain about this system, and I have correspondingly a very low entropy associated with that system. Alternatively, maybe I don't really know what's going on. I say there's a lot of possible microstates, they're all roughly equally likely. That's low certainty, high entropy in this case. One thing that is kind of like a misgiving that a physicist might have about this is it seems to be subjective. Well, what if I, for example, look around the room and say, aha, the gas is roughly equally distributed. Meanwhile, omega goes around measuring the exact position and velocity of every single atom of gas here and says, I know exactly where this is, there is zero entropy. We could have two observers with slightly different knowledge giving different entropies. That isn't ideal, but we'll see why this is not quite so bad as we'd hope, or as we might fear. So given these two views, you might say, well, they probably don't have anything to do with each other because they seem so different. They do agree exactly in one particular case. So if you give me some macro state, call it omega, I can say, well, let's assume that I have a uniform distribution over that macro state. So I'm just going to have some indicator function, which is 1 when we're living on that macro state, 0 otherwise. And the normalizer is dividing by the volume of that macro state. So if we do that, the Shannon entropy becomes just the integral of this indicator function times the log of that indicator function. We take 0 log 0 just to be 0, so we're just going to be left with integrating this simple thing over the region where the indicator function was non-zero in the macro state. This is a constant, we can pull it out, integrate everything. This 1 over omega out front cancels, we're just with log of the volume of phase space. Lo and behold, that's exactly what Boltzmann would say the entropy is. So if we assume that we know the macro state and nothing else, all things equal, these two notions of entropy are in fact the same. However, there's a lot of ifs, and generally there's some tension between these two views. So let's consider two hypothetical systems here. So let's imagine we have an open system which is interacting with a thermal bath. So Boltzmann says, okay, we're evolving through some sequence of microstates. These microstates tend to move towards larger macrostates. They don't always have to, but it's overwhelmingly likely that they do. So generally speaking, entropy is going to increase, but it'll fluctuate. You may have downward fluctuations. You might even have very large downward fluctuations very rarely. But generally speaking, entropy will increase if you start at a low entropy initial state. But if we think of this from more of a Gibbsian approach, saying that really the entropy characterizes our knowledge of the system, I know something to start off with. If I'm evolving thermally, there's some noise. The information I have only degrades. Entropy has to increase. There's no way for it to ever decrease. So how does Boltzmann say that we can have actual fluctuations of entropy? Well, Gibbs says there can be no fluctuations, it can only increase. That seems a little paradoxical here. Another system we might want to consider is really thinking more carefully about what an observer is doing if they're making measurements. So if we take the Gibbsian approach and say that really this probability distribution is our knowledge of the system, if we're making measurements, our knowledge is changing. So Boltzmann has nothing to say about measurements. There's still a single microstate the system is in, is still moving through macrostates. The story is completely unchanged. But if we're talking about Gibbs now, I'm allowed to make measurements. I can improve my knowledge by measuring some properties of the system. And as I learn more, the entropy is going down. okay, at this point you should say, I smell sulfur somewhere here, this is definitely Maxwell's demon. And that is true. So you could say, well, the reason the entropy is decreasing is that secretly I have some list of, like a memory bank here, I'm making measurements, writing them down, I'm trading off one resource for a decrease in entropy. Okay, that's one way to argue this entropy decrease is fine. But the question that I'm having here is more of a question of what does Maxwell's demon see? If you are the demon and you're making measurements, what is your arrow of time? If you think of the arrow of time as simply being the direction which entropy increases, you're making measurement entropy is decreasing, is your arrow of time pointing backwards? What does that really mean at that point? So in order to dig into this a little more carefully, I need to import a few ideas from information theory. If my laptop catches up. Okay, so I want to assume we have two distributions. One of which I'll call rho, and one of which I'll call q. So there's this idea of self-information or surprisal. So let's assume just for a moment, just consider distribution of rho. I'm going to be flipping a coin, and it comes up heads half the time, tails half the time. We want to describe how surprised I am at observing some particular outcome. How surprised should I be that the coin comes up heads versus tails? And a good measure of that is simply the negative log of the probability. So if the coin comes up heads, I get negative log 1/2, which is log 2, which is one bit of information. I can say, aha, it came up heads. Alternatively, if I flip two coins simultaneously, probabilities multiply, logs will then add. I'm twice as surprised. So the reason we have a log here is so that the amount that we're surprised is additive as opposed to multiplicative. And from that, we can then define the Shannon entropy in terms of the expected surprisal. So simply taking the average over all outcomes, we have how surprised we are on average. So if I flip the coin a large number of times, how surprised am I? If it's a fair coin, I'm always surprised by one bit. Take the average, one bit of surprise. So that's fine. We want a slightly different quantity here if we're going to be talking about Bayesian updating. And that's going to be the cross entropy, which at first seems a little strange. So I need to involve two distributions here. So one of which is what we're going to call the ground truth, and one of which is my belief. So let's say you have a loaded coin. It comes up heads 75% of the time. I don't know that. You flip it, it comes up heads. I say, aha, I'm surprised with one bit of surprise, because I think it's equally likely to be heads or tails. You, however, say, well, actually it's likely to be heads and actually not that surprised. We keep flipping it. I keep being surprised by the number of heads that keep coming up. But you aren't, because you know that it should be coming up heads more often than tails. So this is what happens when my beliefs are out of sync with the actual ground truth. So in this case, I'm constantly surprised based on my beliefs, the coin being unloaded. So that's what I'm using in terms of the self-information here. But what I'm actually averaging against, or sampling from, is the truth, that I have a loaded coin here. So that defines the cross entropy between two distributions. Effectively, how much I'm surprised given I think the truth is Q when it actually is rho. Sort of relating two distributions. And a closely related concept is the relative entropy between rho and Q, which is just a difference between this cross entropy and the actual entropy. So you can think of this as effectively how much information you need to distinguish my distribution Q from the distribution rho. So if there's a relative entropy of 2 bits, I just need 2 bits of information to transform from one distribution to the other. It's worth digging into the cross entropy a little more carefully and realizing it's really the sum of 2 independent pieces. I can rewrite the cross entropy as the entropy of the sort of ground truth plus the entropy from my false beliefs. So it breaks up into 2 separate components. So really what we're saying with the cross entropy is there is some underlying uncertainty, this red distribution. I can't get rid of. There's some entropy associated with that. But because I don't know that this is the distribution I'm supposed to be using and I'm using the blue, there's an additional cost I have to pay for using that wrong distribution. That's the relative entropy. So there's much more information-theoretic interpretations of these relations to optimal coding, but for today, that's more than enough for what we're going to need. So I'm going to be talking primarily in the framework of stochastic thermodynamics. And the picture I have here is that I have some small system, which may or may not be inequality. So this could be either a piston of gas with a large number of gas molecules, or maybe a piston with maybe 3 atoms of gas. Can't take the thermodynamic limit there. And this system is going to be embedded in a much larger heat bath at some inverse temperature beta. Everything I'm going to do today is classical, so just assume we have classical gas, classical heat bath. So this heat bath, in principle, is governed by deterministic equations of motion. Same with this cylinder I'm interested in. In principle, the entire universe is deterministic. There's no probability anywhere. Once you know the microstate, you know the future infinitely far forward in the future or past. Of course, in practice, you can't really do that. The best example of this is actually Brownian motion. If I put a small bit of dust on a surface of water, it appears to move randomly. If I really knew the position of every water molecule in that pond, I would know exactly where that particle of dust is going. I can't do that, though. So as a result, what we're going to do is just coarse-grain away the heat bath and say that the system appears to evolve stochastically. So we're kind of cheating here and saying that we can't possibly keep track of every degree of freedom. We're only going to focus on the ones we care about. I have a tiny piston, which I'm trying to keep track of, and an immense heat bath, I can't. The piston appears to evolve in some stochastic manner. And generally speaking, we're going to want to interact with the system. So, for example, we might want a control parameter, such as the position of the piston. So I can potentially vary that as a function of time. Think of doing an experiment where I say push the piston in slowly or take it out slowly. And because we care primarily about non-equilibrium systems, we're going to do this in some finite amount of time. We'll start at some time t0, run until time tau, and we'll make a measurement and look inside the box and see where we're at. So if we're thinking of that, ignoring for a moment the measurement part, I start the system in some initial state. And I'm going to let this evolve stochastically. So there's some distribution over the microstates at the initial time. And there's some transfer function which is evolving my system from some initial microstate x to some new microstate x prime, evolving me in phase space. Generally speaking, this is dissipative, so we're sort of enveloping more and more phase space because I know less and less about the system. For thermodynamics, though, we want to have a concept of irreversibility. I need a sense in which I can talk about the reverse of an experiment. So let's imagine an experiment where I'm dropping an egg. I start with an experiment where I have an egg in my hand. After 2 seconds, I turn it over. The egg falls and splatters on the floor. Clearly irreversible. You can't unbreak an egg. So what is the reverse of that experiment? So the trivial reverse is I reverse the position of every atom in the universe. The egg miraculously reassembles, flies up to my hand, and I turn my hand over and catch it. In that sense, what I just did is reversible. But this is reversibility in the same sense that, say, classical mechanics is T-symmetric invariant, or quantum field theory is CPT invariant. That's not really what we care about. I dropped the egg, it shattered on the ground, it sent energy and shock waves into the earth. That's not coming back. So what you really care about is just reversing the degrees of freedom you have control over. If I switch the direction of atoms in the egg, for example, and in the reverse sequence sort of turn my hand over at the same rate in the reverse direction, the egg would just sort of sit on the ground, I'd turn my hand over, nothing would be there, which is what we usually mean by irreversibility. Alternatively, if you're thinking of this like a softball, maybe I throw a ball, it gets partway to the door. I flip the momentum of the ball, it will then fly back to my hand just in time for me to catch it, because it was a perfectly reversible thing. There was no large increase in entropy. So what we can do now is define a conjugate dynamic, where we're going to flip our microstates. So in general, we're going to flip any time-symmetric, t-odd variable. So in this case, just flipping momentum from positive to negative to define a conjugate state. And we're going to define a conjugate experiment where, once again, this is doing your for experiment in reverse. So maybe instead of turning my hand over, I'm just flipping it back over. Instead of putting the piston in, I'm taking it out in the same manner. This evolution is, once again, dissipative because I'm still coupled to a bath. And I didn't flip all the degrees of freedom in the bath to give it the exact information back out. So I keep dissipating energy, and I keep losing information as I evolve in time. Of course, we want to compare this with our initial state, so we flip it one more time to get a fully cycled distribution. So the full framework here is we start somewhere, we evolve stochastically, we can flip it, think of doing a reverse, and then flip it one more time so we're at least in the same ballpark as where we started. So if this was in fact perfectly reversible and there was no loss of information or energy, we just made a perfect semicircle up here, flipped, made a perfect semicircle, and this blob would sit exactly on here. But clearly they don't. We've lost energy, we've lost information. So where does Bayesian updating fit into all of this? So I want to be making measurements, because I want to have an observer, I want to talk about Maxwell's daemon, and we need a scheme in which to actually include measurements with these probability distributions. We're going to take the sense that the probabilities that show up in the Gibbs distribution are going to be actually our knowledge of the system. And I'm going to assume for the moment we have classical back reaction-free measurements just because it makes life a lot easier. For a classical system, this is fine. If it's quantum mechanical, you can't really make this approximation. And given a measurement outcome, we then need to update our knowledge about the system. So we do this using Bayes' theorem. So we start with some prior, maybe some knowledge over what microstates we think we're in. We have some measurement outcome B, and using the likelihood and marginal likelihood, we can define an update factor and get a posterior, which is where we think we are now knowing what the measurement outcome is. We now update on the fact that we know something new about the system. The thing about Bayesian updating, though, is it doesn't have to be applied at just the time we make the measurement. It applies to everything. We can Bayesian update on whatever we want. So let's consider a really simple example here of particles sort of diffusing in a box. Maybe at the very initial time, either all my particles are on the left-hand side, or all of them are on the right-hand side. Equal odds. And then I take out a divider, and I let them sort of diffuse back and forth. And as they diffuse, almost equal amounts will be on each side. Not quite, because I didn't give them quite enough time to fully divide. But as they continue to diffuse, we'll approach roughly 50-50. But let's say I stop at that point, and I throw in the divider and say, I measure which side has more particles, and I say, there are in fact particles on the left-hand side. At that point, I do an update and say, aha, I know that the particles are on the left-hand side rather than the right-hand side, so this is what part of the distribution I care about. We make a measurement, and we perform an update. We can throw away the rest of the distribution now, updating on our knowledge that the particles, in fact, are living on the left-hand side of the box. Given that knowledge, we can also update what we knew about the initial state. We have information, we might as well apply it to everything we can. Which then tells me that, sure, initially, I was actually more likely to be on the same side of the box than the other side. There's still some chance I was on the other side and happened to float along all the way over, but it's simply less likely. So we can update both the actual moment in time when we make the measurement and things that happened before it, given this measurement outcome. So let me create a diagram here of the distributions we care about. We start with some initial distribution over microstates, call it rho 0 of x. And we have some evolution function, pi sub f, which evolves us forward in time from x to x prime. And given that, we can define some final distribution at time tau over x prime. We do some forward experiment and it ends. We now have some distribution over where we might be. I can then introduce a reverse protocol like we discussed before and evolve backwards in time, or at least under a reverse conjugate dynamics, and define a distribution which has now been cycled around. And I can try to compare this to my initial to determine how out of equilibrium I am. But I now want to actually include the fact that we can make a measurement. In particular, we're going to evolve for some time tau, and at the final time, we're going to actually look inside the box and say, aha, this is what the system's been doing the whole time. If I do that, I need to update. So if I know the probability of getting a measurement outcome m, given some microstate x prime, I can then do Bayesian updating for both the final distribution and the initial distribution. So now I have the probability of ending up at some microstate given my measurement outcome. I also know the probability of having started originally in some microstate x given my measurement outcome. And it turns out even the dynamics are now updated. I have the probability of transitioning from x to x prime given that we've updated. That might seem a little weird at first, but you can think of it this way. If I have Brownian motion, I'm equally likely to be kicked to the right as I am to the left. If I find myself very far on the left side of the room, it's likely I got kicked to the left a lot more times than to the right. So if I update the dynamics, it simply says that this is more likely to kick me to the left than to the right, just given my update. The reverse is unchanged, though, because it happens after the measurement or without a measurement. We're still doing some reverse evolution. The cycle distribution changes, but only because this final distribution is now different. We've updated, we cycle it back. It looks different, though the evolution is unchanged. So at this point, we have almost everything we need. I'm just going to define one last object and define a joint distribution over the initial microstates and final microstates, given this measurement outcome. So we now have some joint distribution function over initial and final in the forward and initial and final in the reverse, just multiplying them together. So at that point, we can just use the usual approach, which was pioneered by Kawai, Karando, and Van den Broek, by looking at the relative entropy and using its monotonicity. Or for those of you that prefer information theory, this is just the data processing inequality. So if I look at my joint distributions in the forward and reverse time, the intuition here is that if the forward process looks very different than the reverse process, that should be telling me something about how irreversible this is. If the forward and reverse look the exact same, this is reversible. There's no sense of time being in one direction or the other. If they look very different, it looks very different going forward versus revert, as opposed to reverse, then there's a sense of time in one direction or the other. We can then coarse-grain by integrating over the final microstates and just look at the initial distributions. So this is just data processing. I'm sort of removing information by tracing out. After doing a little bit of gymnastics with the relative entropies, we can then rewrite this in three terms. The first of which is the relative entropy between the updated final distribution and the unupdated final distribution, the updated initial distribution and the unupdated initial distribution, and some average heat flow given the update. The right-hand side simplifies a little more, where we can simply then get rid of the final states, and we're just left with the updated initial and the fully cycled around initial, telling us the overall irreversibility. So this is actually what we're going to call the Bayesian second law. We have some information-theoretic terms on the left and something related to dissipation on the right-hand side. Okay, so this is all well and good. I just did a bunch of mathematical manipulations, threw around some information theory, but what does it actually mean? So just for a moment, I'm going to assume there's no heat transfer. Ignore the heat for a moment. We're just going to talk about the interesting quantities. The relative entropy is is non-negative. So I know that this dissipation is at least equal to 0. So I have some information-theoretic quantity bounded from below by something that looks like an irreversibility term. If these are very different, this becomes more positive. If they're identical, it's just equal to 0. The left-hand side is related to how much, so this is our irreversibility post-updating. The left-hand side is related to how surprised we are. So thinking back to the cross entropy, the cross entropy between, say, our final and an updated final distribution is how much I would be surprised, given that I don't know the measurement outcome, say that I'm placing bets based on the unupdated distribution, given that someone else has made the measurement, and there is some true distribution which I'm ignoring at this point. So it's sort of related to my mismatch between my unupdated beliefs and my fully updated beliefs. So this change in surprise is going to be strictly positive, non-negative. So a little more carefully, regardless of the measurement outcome n, we're always more surprised to learn the microstates at the final time tau than at the initial time t equals 0. So this is saying that there's no measurement outcome where we'll be less surprised in the future. In the sense of cross entropy, we're always going to be more surprised in this particular sense going forward in time than in reverse. So this is a reasonable approximation to what we'd want to be an arrow of time. Okay, I kind of cheated here insofar as I put in stochastic dynamics to begin with, but at least this is increasing in time monotonically. So we can rewrite this in two other forms, depending on what you want to talk about. So if we want to get this back in terms of change in entropy, we have to make a decision here. Final entropy is relatively clear. What I mean by the final entropy at the end of the experiment is, what is our final state after I've done the updating? That's relatively clear. But what's the initial entropy? Well, there's two options here. Option one is we say, well, the initial entropy is what we started with before we did any updating. I had some knowledge, I thought this is the entropy, how much did my uncertainty change? That's his first quantity. Alternatively, we could say, well, actually what I mean by the change in entropy is now knowing what I do now at the very end, how would my uncertainty have changed if I knew that measurement outcome? So what is the difference between the updated uncertainties? So two different notions here, depending on what exactly you want to be getting at. And that leads to two slightly different inequalities. So this first one is a little unfortunate insofar as the third term on the right-hand side is kind of a mess. But we're left with what looks something vaguely like a second law. We have some change in entropy involving heat, and two information-theoretic terms here. So we have a term which is trying to increase the entropy production based on how reversible or irreversible a process is, and something that allows us to potentially decrease entropy production based on how much information we gain. This is actually just the information gained from the measurement, from an information-theoretic perspective. But we have this really weird object here, which involves a difference of two distributions and a log of this other distribution. It's not ideal, kind of messy. But at least if we average over measurements, this one will disappear, and similarly for the Boltzmann case, where we have a constant distribution over a macro state. A more clean expression shows up when we want to talk about the difference between the updated entropies. In that case, we get three purely information-theoretic terms, where in addition to having this negative term based on the update at the final time, there's another term playing off of it involving how much we learned about the initial state due to that measurement. So there's a question of effectively the net gain of information between that final initial time shown up on the right-hand side. So let me return to the puzzles I started with. So let me start off with the puzzle of why does the Boltzmann formulation of entropy allow for fluctuations, but the Gibbsian approach naively doesn't allow for a fluctuation? So let's assume we're starting in some macro state, and we happen to fluctuate into a smaller macro state. So this is exactly when Boltzmann would say, aha, your entropy has fluctuated downward. So what we're really saying then is we start with some initial distribution, which is flat over a macro state. So we have a uniform distribution over some particular macro state omega. If we have that, then that third term, this kind of messy term that we had on the previous slide, will end up vanishing. The reason being is that if I'm looking at the log of that initial distribution, it's a constant. I can factor this out. The remaining terms have to integrate up to 1. This distribution is normalized, integrates to 1. This distribution is normalized, integrates to 1. This whole thing vanishes. If you do that, what we're left with is that the change in entropy between the unupdated initial state and the fully updated final state is bounded by an irreversibility term minus an information gain term. This is sort of the usual story from Maxwell's demon. We're allowed to have decreases in entropy if we're gaining more information than is being dissipated by the bath. Entropy can then go down. The reason that in the naive Gibbs approach you don't see fluctuations in entropy is simply that you're not doing any updating. The reason that entropy goes down for Boltzmann is that you've gone from a large macro state to a smaller macro state. That tells you something. You have to say, aha, I'm now in the smaller macro state. If you don't do that, then the Gibbsian approach gives you sort of garbage because you're not saying that you've actually imposed the fact that you've ended up in a smaller macro state. And similarly for the other formulation where we're looking at the updated final versus updated initial entropies, we can now just use the fact that the information gain at the final time must be at least as large as the information gain at the initial time. This is once again the data processing inequality. I'm sort of learning something at the final time, and I'm trying to propagate that backwards through a lossy channel, so I'm learning less and less as I move back. This tells me that I can bound my entropy production by an irreversibility term minus some other number. It's going to be positive, and depending on how much information gain you have, this could be a very large positive number, allowing you to have a negative entropy production. So in both cases, you can have fluctuations of negative entropy, assuming you're doing the Bayesian updating correctly. So there's still the question about the arrow of time. And, well, how resolved this is depends on how willing you are to buy the assumptions. So let's assume we have a closed system with an observer, and we're trying to imagine what does the Maxwell's demon see? You're not looking at your own memory, you're just looking into the system. So, as I just stated, in general, we're allowed to have negative fluctuations of entropy if we're allowed to do updating. And if you average over all the possible measurement outcomes over possibly many realizations over a long period of time, on average, that change in entropy is going to be less than the change in the unupdated entropy. And in general, it might be a lot less, potentially negative. So in that sense, the entropy really is going down in the system, and you might worry about the fact that the arrow of time is now pointing in reverse. The system appears to be evolving backwards, which seems a little unusual. However, we at least have some indicator that's always increasing, and that's this cross entropy quantity. The cross entropy between the updated and unupdated distributions is always greater than or equal to 0. So at least gives us something that's increasing in time. Okay, there are only two primary complaints about this. One is this is not dynamical, which is kind of unfortunate. Because at least in the entropy approach, I could think about entropy increasing as a function of time throughout the experiment. This cross entropy is only properly defined once I make the measurement at the end. Once I've made the measurement, I can then sort of retrodict and say, aha, I have an arrow of time. I can't say that, oh, there's really an arrow of time the whole time until I've actually made the measurement. And the other thing is, I've already cheated a little bit and put the arrow of time in to begin with. I've been working in the framework of stochastic mechanics. I've integrated out some degrees of freedom on my heat bath and sort of put in dissipation, which gives me an arrow of time to begin with to some extent. So if you're in a perfectly closed system with no bath at all, then this delta H, this change in cross entropy, ends up being exactly 0. Well, it's not great insofar as there's no arrow of time, but it could be worse and the arrow of time is not pointing backwards. So it's a small victory in that sense. And as before, if we're thinking about this, it's really telling us that we're really always more surprised to learn microstates as we go forward in time, regardless of what measurements we're potentially making. So that's a fair amount about inequalities, but what about equalities? Because if we're looking at non-equilibrium behavior, things like the Crookes fluctuation theorem, the Jarzynski equality are relatively powerful tools. Can we get something else out of them by taking a Bayesian approach? So if you're thinking about something like the Jarzynski equality, you usually cast in the form of you have some reverse realization, some distribution over that, over your forward realization. You average it over all forward realizations. In general, this is equal to 1, except for potential caveats about strictly irreversible paths, in which case some constant that's less than 1, between 0 and 1. And this is an equality, which in some sense is stronger than the second law, insofar as you get the second law as a consequence of this. But as I said before, we kind of cheated and put in dissipation to begin with. So it's not strictly stronger because you've already assumed the second law. So if we think of taking a Bayesian approach, we can instead talk about the conditional forward reverse distributions being averaged over conditional paths. So simply saying, I'm going to collect statistics, but I'm only going to talk about paths which gave me a specific measurement outcome M. I'm going to aggregate those and take this expectation value, it will give me some other number, potentially less than or equal to 1. And what this does is it's effectively a partition. Even if you have paths which are potentially strictly irreversible, if I integrate over these constants, these BMs, averaged by the weight of some particular measurement outcome, its likelihood, I exactly get back the A that we have for the Jarzynski equality. So in this sense, I've just partitioned up my fluctuation theorem into a bunch of individual fluctuation theorems. In this sense, we now have the fact that the Jarzynski equality holds not just for a given measurement, for all measurements put together, but each individual measurement outcome on its own conditioned on that outcome. And if we recast this in terms of potentially more interesting thermodynamic quantities, we can talk about realizations along a specific path. So I'm thinking about the probability of a final state given updates, or initial state given updates. I can recast this equality in terms of the point entropy of the final updated distribution minus the point entropy of the updated initial, some heat transfer, and then an information-theoretic term. So in this case, it's going to be the mutual information, point-wise mutual information between the measurement and the final microstate, conditioned on the initial microstate. Similarly, if you instead prefer to work in terms of unupdated objects, the information-theoretic term becomes the point-wise mutual information between the measurement outcome and the initial microstate conditioned on the final microstate. These differ slightly from the previous versions found in the literature, particularly from Takahiro Sagawa and Masahiro Ueda, is you get slightly different information-theoretic terms given their partitioning of the inequality than what we're getting here using this sort of Bayesian approach. So I've been talking primarily about entropy, a little bit about information-theoretic quantities, but if we're talking about physics, we usually care about things like work and heat and other quantities. So can we apply a Bayesian approach to those? So let's try that. If we're thinking about this for a moment, we can relate change in work, the work done on a system, the heat, and the change in energy through the first law, just through a simple equality that we have to have energy conservation. And we need one more quantity, and that's the free energy. So if we're in equilibrium, usually what we want to do is say the free energy is simply the Legendre transform of the energy with respect to the entropy. So we just have E minus 1 over beta S, defining the free energy. That's fine in equilibrium, but I want to talk primarily about systems out of equilibrium. There are a large number of ways you can define a free energy out of equilibrium. People will argue about this extensively. I think there's actually another talk specifically on this topic. I'm going to use one specific definition of the non-equilibrium free energy. If we take apart this free energy, this is really the expectation value of the energy, and then the expectation value of a surprise law. So if I think about this, the free energy is really the expectation value of the energy at a given microstate plus 1 over beta times the surprise law of getting that specific microstate. And I'm just going to average this quantity. So I can think of this quantity living inside this bracket that I'm taking the expectation value over as being some fine-grained free energy. Sort of a free energy defined at a given microstate, given that I have some energy function and some distribution over microstates of what I think the probabilities are. I can have define a sort of function defining the free energy at each given microstate. If you give me that definition, then we can work with updated free energies. So I can recast all of the previous results in terms of change in free energy. So we can define sort of the work done by the system, given updates, as being bounded from above by a change in updated free energies and some information-theoretic terms. So this is basically, once again, a Maxwell's demon type expression where we have some net information gain and then some net drop in free energy bounding the potential work we can get at. This is in a slightly different context because we've now been doing a more Bayesian approach and talking about this in a single trajectory kind of level. Similarly, we can talk about mixing the fully updated or unupdated free energies. Because the question is, once again, what was my initial free energy? Was it the free energy that I thought I had before I knew anything else about the system, before I knew any measurement outcomes? Or was it the free energy that I have once I made the measurement and I'm looking back into the past saying, that was the free energy I had at the beginning? And once again, we find this kind of ugly expression if we try to mix them, where we have this difference in the updated and unupdated initial distributions times sort of this functional that shows up. And once again, there's sort of the same caveat with equilibrium distributions, where any equilibrium distribution has the property that this free energy functional is constant across it. So this becomes a constant, I can pull it out, this entire term vanishes. So whether or not this term is physical really depends on what type of distributions you're interested in. If you're always interested in starting from an equilibrium state, that term vanishes. If you're interested in going from non-equilibrium to non-equilibrium, then you have to start worrying about that. So just to kind of wrap up, there's sort of these two paradoxes we saw in terms of the Gibbs and Boltzmann approaches, in terms of error of time and also whether or not entropy is allowed to fluctuate. And taking a Bayesian approach, we have a little more insight into why these contradictions appear. The Bayesian approach kind of hints to us that if we're thinking of error of time, maybe change in entropy is not necessarily the best way to define an error of time. Maybe cross entropy is sort of a more natural manner to do that. And that in terms of these fluctuations, the reason that the Gibbsian approach naively appears to disallow decreases in entropy is because we're not putting in updating. While the Boltzmann approach has no sense of updating, it's allowed to have potential fluctuations downward. And we found that by including these Bayesian approach, we were able to modify a number of expressions related to both entropy production and to the integral fluctuation theorems to recast them in a Bayesian light. So we now have fully updated expressions conditioned on specific measurement outcomes. So we can now talk about entropy production along a particular path, given that we have some particular measurement outcome. Or alternatively, an integral fluctuation theorem conditioned on the fact that we get some particular outcome. And similarly, it's not just entropy we have to talk about. We can talk about work, free energy. They also fit into this framework. So, thank you.
Questions? Yeah, I can see. Okay. Questions?
This is probably a very naive question because I don't know anything about this, but I always think of Bayesians as highly subjective.
Right.
And I like to think of entropy as something in the world. And so are you actually trying to tell us what entropy is, or are you trying to give us a mechanism for wonderfully tracking entropy? Like there's something objective in the world, entropy, and you have a wonderful method of tracking it. Is that the point?
I would say that's not quite the point. So
Okay.
I would agree that the Bayesian approach appears more subjective on its surface. But I would argue, potentially dangerously, that entropy itself isn't really objective, even from the Boltzmann. Is not.
Is not.
Even from the Boltzmannian approach, I disagree. Insofar as I'd say it really depends sensitively on your macro state choice. That, once again, there's kind of the argument between frequentists and Bayesians, where a Bayesian says a high at priors, and a frequentist really sweeps that under the rug. The question is, where are your priors in the Boltzmannian approach? It's really the fact you've imposed macro states. Where did you get them from? Why those macro states and why not others? So if you're worried about subjectivity in that sense, I could choose pathological macro states and have the entropy appear to decrease. It's simply the fact that, at least usually, in the way that we define them, it results in sort of an increasing entropy. So I'm not so worried about the subjectivity in that sense, because I feel like both of these are subjective, even though the Boltzmannian approach feels more objective in that sense.
It's just a footnote to that. So the Boltzmannian is adding to, like I said, not just the choice of macro states, but taking a particular measure on the energy surface to choose to measure the size of those macro states. So there will also be there'll be measures on an energy surface according to which what we think of as the equilibrium state has the largest measure. There's measures on which that's the smallest, tiny.
Right.
On the question, so this is we have a tradition around here that like a new question you hold hand, a follow-up on a point made is a finger. Fingers always, if I'm chair, fingers always take precedence over hands.
Unless it's the middle finger.
We don't do that around.
We don't do that.
Yes.
Finger, and I can push back a bit on this, on what you just said about Boltzmannian being subjective, because there seems to be, just because something is relative to a choice of variables or a choice of carving up your base space into macro variables doesn't really make it subjective. And in fact, we make these choices all the time when we describe systems. We always chop up our world and reference frames, and we define our entities relative to these relative to reference frames, for example. This doesn't make them subjective necessarily.
Right. So I think that subjective versus subjective is, I guess, kind of a subjective approach in that sense, because it really depends on what you're talking about here. So if I really think I am like omega, I have perfect knowledge, I could choose macro states that are, in fact, just the micro states themselves. Everything has equal entropy. It never changes, because I'm just going micro state to micro state. Similarly, on the side of the Bayesian updating, if I'm once again omega and can measure exactly where I am, I have no entropy, because I can say I'm exactly in this micro state. There's nothing to learn at that point. I think it really is a question of what your knowledge could be. I think in practice there's not much difference between these two. I think it's simply a question of when you're pushing these to extremes, what happens. Because if you're saying that I have some potential resolution in terms of distinguishing macro states, in a Bayesian sense. Sorry, in a Boltzmannian sense. You say, okay, I'm going to carve this up into potentially pressures that I can measure. Say, maybe I can only measure some accuracy, I'll call that a macro state. On the Bayesian side, that's roughly the width of my measurement. I'm saying I can update and say that the pressure was roughly between these 2 points, and I'm thinking of performing an update that roughly corresponds to the same macro state. So I'd say that they're sort of equal in that sense. So I'd argue that if you want to call one objective, they both have to be equally objective. At least given that we're assuming 2 observers have access to both the same equipment and knowledge. So of course I could choose, for example, being Bayesian, a pathological prior, put 0 weight on some spaces. That could lead to different results. So I agree with that. But assuming I don't assume a pathological prior, we both have access to the same set of evidence and same measuring equipment, we'll also agree, at least insofar as we agree in terms of carving out phase space.
Right, sorry. But there's a matter of fact that the system is going to be microstate. You agree about that?
I mean, yeah, in the sense of this system has a particular microstate. If you can measure a particle, sure.
Yeah, so I made a remark in my talk that I prefer to not use this word, this terminology subjective. And I think that this is a good illustration of why, because subjective, in least some circles, suggests that, well, it is just like a matter of personal whim or personal taste. Like you prefer butter tarts with raisins in them or not. And that's got nothing at all to what you're talking about, because what you're saying is relative to a probability distribution. Well, I can't arbitrarily choose to have, I want to have perfect knowledge of the state of the room. Well, I can't do that, right? And as you said in your response to Karina, it has to do with the means you have of access to information about the world. And so there is an epistemic access aspect to everything you're doing, but subjective is the wrong word, I think.
Yeah, I suppose maybe you'd say like dependent upon your apparatus, or
Means relative depending on your apparatus, on the apparatus you have available to you.
Yeah. So I think I would agree with that in terms of that's what I really mean by subjective. It depends. It's not something I can say from on high. This is how you do it. It really depends on what your equipment is, and to observers with different abilities to disagree on what the appropriate measure would be in that sense.
More questions? Yes.
There's one in your talk where you were referring to the cross entropy and how it always increases.
Yeah.
And you said this was not dynamical.
Right.
I took that to mean that at the time I thought you were trying to say that we would have preferred if entropy increased over time, which I read as a kind of commitment to the notion that entropy is a property which a system which we expect to increase over time. But given your epistemic interpretation of entropies, what exactly do you have in mind here? What is it that you wanted, that dynamical increase?
Okay, so I suppose dynamical isn't quite. Yeah, so I'm trying to get at a kind of subtle point here, so I suppose my language isn't perfect here. If I'm thinking of the entropy, and I'm thinking this is a process between time t0 and t tau, right, and the experiment making a measurement. At every given moment in between, as I'm sort of evolving the system, I can talk about what I assign as my probability distribution over microstates. I have some well-defined entropy at each point in time, given my knowledge. And I can say that that entropy is increasing because information like degrades. But then I make a measurement, and I say, oh no, my entropy suddenly falls, because now I know something else. It's only once I make that measurement, which I can now say, let me look back and see what my cross entropy was. So then I can now say, aha, given what I know now, what would my surprise be given some particular microstates outcome? And I can now plot my cross entropy as a function of time. That is increasing now. The problem here is I can't actually sit down and plot that until I've made the measurement. So it's not dynamical.
What is that problem for your epistemic?
I think it depends on what you want. So if you want to say we have some quantity which is sort of dynamical, not depending on the observer or their measurements, it increases in time the way we hope that entropy does in that sense.
I thought you didn't want that.
I'm fine not having that. It depends on, yeah, I'm saying it depends on what you want out of this. So you're saying all that we really care about is for an observer making measurements, is there some quantity which is increasing in time. I can say, aha, cross entropy is greater than or equal to 0 always. So as you make measurements, I want to say this is increasing for you, and there's some sense in which this is measuring time for you. In that case, I'd say this is perfectly fine. But the question is if you want to tie that into the dynamics of the system, and not just the observer making measurements. If that makes sense, or is not quite clear.
Well, I guess what I'm confused about is, it seems like that latter statement, tying this decrease to the dynamics of the system would only make sense if you thought that the entropy was a property of the physical state of the system.
Yes.
But given that you do not think that the entropy
Yeah,
is a
so I
property,
guess once again,
then it's not a problem. It shouldn't be considered a problem.
yeah, I suppose this is sort of to cut off potential complaints about, well, shouldn't entropy be a property of the system? So I would agree.
I think you cut that off. I agree with you.
Yeah.
Say, no, you're mistaken about it being on. It's epistemic. Done.
Yeah, so I agree it's epistemic. So I'd say that in that sense it's done.
Okay.
Unless you were hoping that there was some ontic object I could put in there, in which case I'd say, well, I don't know what that ontic object is, because it's not this. And I don't think it's entropy either, and I don't think there is any such object.
More questions, comments?
This is a terminological comment. Actually, it's a historical comment too. So you thought this quantity minus rho, it gets called Gibbs entropy. So you follow totally standard terminology. We call that Gibbs entropy, and calling a Gibbsian approach one that applies it in all kinds of situations, including non-ordering decision regions. This is a historical note. Gibbs argues for treating that as an analog of thermal entropy only for a system in equilibrium with a heat bath, and his argument crucially depends on the thing having a canonical distribution. And in fact, he considers the possibility of using it as a measure of distance from an equilibrium for an isolated system, says, well, no, that doesn't work because it's conserved under evolution. So treating that as an entropy outside for anything else but a cannot be distributed system in contact with heat bath isn't Gibbsian in the historical sense, but I don't know what to do with the terminology because when you use it, it's become completely standard terminology.
Which is why I called it like Gibbs/Shannon, because it's roughly how we think of it nowadays. And as I sort of caveated at the beginning, these are kind of stuffing words into people's mouths historically because it's not quite, it was a little more fuzzy than what I'm making out to be here.
So I don't know what to do about the terminological thing, but so people should be aware that some of the absurd consequences of treating like an entropy in various situations, are things that you can attribute to the historical. Maybe theologians distinguish between the historical Christ and the Christ of faith. So maybe there's a historical gifts and the gifts of mythology.
Owen has, before your last remark.
So this morning when you suggested, or strongly, that we should say neo-Boltzmann.
Could you speak up slightly? I have hard hearing.
This morning you suggested very strongly we should say neo-Boltzmann.
Yeah.
I'm talking about kind of Boltzmann framework of Albert and Boltzmann, because that's not really what Albert or Boltzmann said.
Right.
Maybe we should describe this as the neo-Gibbsian framework, because it's not really what Gibbs said, but it's the development of it in the spirit.
Okay.
Now, were there any other questions? I want to see if there's agreement on a terminology change introduced to the field. Hands up if you agree. Okay, it's not a majority. Other questions? Well, thank you very much.